Hello. In this video, we will cover section 4.2, which is on the correlation coefficient. The correlation coefficient is a number that measures the strength of the linear association. A linear association is required. The correlation coefficient is represented using the letter R. It is always between -1 and +1. Both the value and the sign, positive or negative, have important information. If the value of R is close to -1 or +1, then the association is very strong. If close to 0, the association is weak. If the value is positive, then the trend is positive. If the value is negative, then the trend is negative. The following pages show examples of scatter plots of coefficients ranging from +1 to -1. All right, so let's take a look at these. All right, so this is what a +1 correlation coefficient looks like. It's every single point from the scatter plot is perfectly on the line itself. Okay. Meanwhile, 0.98, you can see that the points are not all on the line, but they are very closely clustered around the line. 0.72, we've got the strength of the correlation has weakened, right? So you can see that the strength is measured by the vertical distance in the scatter plot. And so you can see there is a fair amount of vertical distance there, but you can still see a clear trend here, okay? And so that's why this is still a relatively large number, right, above 0.5. So when we get down to 0.5, you can kind of start to see some correlation. It can be kind of difficult, sorry, to see that there is a correlation there, but there is still a bit of a trend to the points, okay? You can kind of go through and maybe draw a line about like this, right? About like that. And the points would all be clustered around that line. However, at a certain point, it's very difficult to tell whether there is a trend at all. The points are just scattered all over the scatter plot. And then when you get down to, and that's a 0.19 is a very low correlation coefficient. That's why we're having trouble identifying a trend there. And of course, 0 is that there is no correlation. This is just a bunch of dots. And then there's 0 again. And then so when we get to negative correlations, so negative 0.35, this is a small number, so they're not, the points are not very well correlated, but you can kind of still see there's a downtrend in there. And the negative is what measures that there's a downtrend. Okay, and as we increase the size of the number ignoring the negative, the trend becomes stronger, and then of course that negative is there to tell you that the trend is negative. All right, so we've got this is definitely much clearer that there is a trend there. Negative 0.79, they're getting closer and closer to the line. Negative 0.9, you can very clearly see, and then -1, the points themselves are exactly on the line. So let's look at the correlation coefficient in context. So some examples. All right, so college admission offices sometimes report correlations between student SAT scores and their first year GPAs. If the correlation is high, this justifies using the SAT to make admissions decisions. Why? Because a high correlation would indicate a strong association between SAT scores and academic performance, right? Which is what a college wants. A positive correlation means students who score above average on the SAT tend to get above average grades, right? That's a good thing. Conversely, those who score below average on the SAT tend to get below average grades. Okay, so the positive correlation tells us that the SATs and grades are linked, which tells us that if we were to accept students who have high SAT scores, they're likely to be successful. And if we accept students with low SAT scores, they're less likely to be successful. All right, and then finally, when it comes to interpreting something like this, note that we use the term tend to. All right, so because there's always going to be exceptions. There's going to be some students with low SAT scores who do very well, and some with high SAT scores who struggle. All right, so correlation does not mean causation. So this is a common phrase that is thrown around that you may have heard before, the idea of correlation and causation. So the two are different. So research questions often involve cause and effect. For example, does giving a patient a new medicine improve their condition? So the cause is you give the new medicine, the effect is that improves their condition. Or does changing a tax law improve the economy? Right? The cause, you change the tax law, the effect, you improve the economy. People like cause and effect relationships. All right, so proving a cause and effect relationship, which is what we call causation, between two variables requires that the two variables are correlated, but it also requires additional steps. So it's not enough to have correlation. All right, and we can see why by looking at an example, right? So one reason is that correlated variables could both be the consequence of a third variable, which was the cause. For example, ice cream sales and violent crime are closely correlated. That isn't because ice cream sales, that isn't because ice cream causes violent crime, or that violent crime causes people to want ice cream, but that hot temperatures affect both variables separately. Right, so you have to be very careful when it comes to going through and interpreting correlation as causation. So correlation does not mean that there is a cause and effect relationship. It just means the two things are related, they're correlated. All right, so we've got some characteristics of the correlation coefficient that you need to know. So the order of the variables does not change the value of the correlation coefficient. This means that if the correlation between life expectancy for men and women is 0.977, then the correlation between life expectancy for women and men, right, we change the order, is also 0.977. Adding a constant or multiplying by a positive constant does not affect the correlation coefficient. So let's look at an example. So suppose the correlation between the heights and weights of 6 women is 0.881. If all 6 women wore 3-inch heels, which would make all of 6 women 3 inches taller, the effect that has is that it shifts the points in the graph. It shifts them, right? But if you just shifted all of the points on the graph, that's not going to change the correlation coefficient. The correlation coefficient is how the points are clustered around a line. If you go ahead and move the points around, they're still going to have the same cluster. It's just going to be, they're going to be clustered around a different line. Okay, and so the clustering is what you're measuring with the correlation coefficient. And so moving the points by adding or subtracting values, or even multiplying by a positive, is not going to change the correlation coefficient. Okay, and then here's an example here. This example, it shows the men and women life expectancy being swapped, right? And so they're clustering around different lines. These are different lines, okay? Although it's a little bit subtle, actually. But the clustering is still the same, and so you'd get the same correlation coefficient if you went through and just swapped the effectively the x and y variable. If you swap the x and y variable, it doesn't change the clustering. Okay, and then this is an example for the height and weight for women. We've got the points, and so there's a 0.881. So the idea is you could draw a line here. If you just took all those points and just shifted them 3 to the right, you can go ahead and draw the line here. It's a different line, but the clustering is still the same. So the correlation coefficient is still the same. Correlation coefficients are unitless. This means that we will get the same value for the correlation coefficient in the previous examples, regardless of whether we measure the women's heights in inches, meters, or fathoms, or even fathoms. All right. And then finally, the last characteristic is linear. The correlation coefficient only applies to linear relationships. If the relationship between the variables is nonlinear, then the correlation coefficient does not apply. To determine whether the relationship is linear, you need to go through and visually inspect the scatter plot of the data to see if the data clusters around a line. So it's not enough to just go through and use the correlation coefficient on some scatter plot that you haven't looked at and get some value out and then start making interpretations about that value for the correlation coefficient. You need to look first. Oh, yes, there is a line here, and then you can go through and use the correlation coefficient. Okay, so, and then here are some examples to go through and illustrate. What are we illustrating here? Oh, that the correlation coefficient for linear versus nonlinear, right? So all of these have the same correlation coefficient value of 0.817. So you can see here the points are clustered around a line. Even here, they actually are clustered around a line. It's just a vertical line. Here they're clustered around a line. You just have this outlier. It's kind of the same thing here. You have this outlier. Well, here, so all three of these would be fine to use the correlation coefficient. But here in the last one, it would not be appropriate to use the correlation coefficient because this is nonlinear. Let's look at a couple examples from the homework. So the first question, the figure shows a scatter plot of birth rate and age of the mother in the United States. Would it make sense to find the correlation for this data set? Explain. So should we find the correlation coefficient for this data set? The answer is no. It would not make sense to find the correlation coefficient because the trend is not linear. All right, and then the next homework example, the correlation between house prices in dollars and area of the house in square feet for some houses is 0.91. If you found the correlation between house price in thousands of dollars instead of just in dollars, and thousands of dollars and area in square feet for the same houses, what would the new correlation be? So if we changed units from house price in just single dollars to house price in thousands of dollars, so we have scaled the house price, that would, in effect, what you'd be doing there is you'd be dividing by 1,000. Okay, so does dividing by 1,000 change the correlation coefficient? No. The new correlation would still be 0.91. Changing units or multiplying the numbers for a variable by a positive constant does not change the correlation coefficient value. Okay, that is the video. Thank you for watching, and I'll see you next time.